Welcome back to Neural Intel. Today we're diving into something pretty interesting, the technical side of instruction-based image editing.
Yeah, and specifically how AI models handle complexity.
You shared this paper, Complex Edit, and it really gets into the nuts and bolts of testing how well these AIs follow instructions when they get, well, complicated.
That's right. It's all about moving beyond simple commands. We're looking at the technical challenges and the advancements needed for more sophisticated edits.
Okay, so the core idea, as I understand it, is that current tests are often too simple, like just remove the car.
Exactly. That's useful, but it doesn't capture real-world needs. Think about wanting something much more specific.
Like change the car to a blue bus and put an ad for an iPhone on its site, something like that.
Precisely. That's got multiple steps, multiple constraints, and that's the kind of thing current benchmarks don't really push models on.
So Complex Edit is trying to bridge that gap.
It systematically looks at how models perform as instructions get more and more complex.
Okay, let's unpack the technical details. How do they actually create this benchmark? What's the process?
It's a pretty neat three-stage pipeline they developed for generating the data.
3 stages.
Yep. First is sequence generation. They use GPT-4o, a pretty advanced language model, to generate a sequence of simple atomic editing instructions for an image.
Atomic instructions,
Right.
is like the smallest possible edits.
Kind of. Think of breaking a complex task down. So for one image, GPT-4o might spit out, add a small ball of yarn, then maybe change the color of the yarn to red.
Okay, little building blocks.
Exactly. They define 24 of these atomic operations, grouped into 9 categories, things like object manipulation, color changes, background edits, lighting, even adding text.
So changing object properties, moving things.
Right, like move the tree to the left could be one atomic instruction under object manipulation.
Got it. So GPT-4o creates this list of basic steps. What's stage 2?
Stage 2 is simplification. They found that GPT-4o sometimes added extra commentary or fluff to the atomic instructions.
Ah, so they cleaned them up.
Yeah, use GPT-4o again to basically trim them down, keep only the core editing instruction, remove the noise,
Makes sense. Keep
Ah.
it focused.
Yeah.
And the third stage must be where the complexity comes in.
Exactly. Stage 3, instruction compounding. This is where they take those simplified atomic instructions and merge them, again, using GPT-4o.
Merging them into one single instruction.
Yes, into one single coherent but more complex instruction. And the clever part is the complexity level, they call it C1 up to C8, is controlled simply by how many atomic instructions get merged.
So C1 is just one basic edit, and C8 is combining like 8 different basic edits into one sentence.
Pretty much, yeah. It allows for a really systematic way to ramp up the difficulty.
The paper gave examples, right? How does that look in practice?
Yeah, they had a good one. Imagine an image with a dog and a white car. Level 1, C1, might be, replace the dog with a cat. Simple.
Okay.
Level 2, C2, could be, replace the dog with a cat, make the white vehicle blue.
Right, adding another element.
Then level 3, C3, maybe adds, make the white vehicle blue, remove the bicycle. Assuming there's a bike there too.
And by level 8, it gets pretty wild, I imagine.
Oh yeah. Level 8 could involve stuff like changing the background entirely, say, to a rainy autumn night, add a specific street light, maybe put some sparrows on a fence. Really intricate stuff.
Wow. Okay. That's a huge difference in complexity. And they use techniques like few-shot learning and chain of thought with GPT-4o to get better results during this generation.
That's right. Few-shot learning is like giving GPT-4o examples of good complex instructions first to guide it.
Kind of priming the pump.
Exactly. And chain of thought encourages the model to sort of show its work or think step by step, which usually leads to more logical and coherent outputs.
And they filtered out bad results too.
Yeah, they had rule-based filters to catch flawed instructions and regenerate them. Quality control for the benchmark data.
Okay, so they've built this benchmark. Now, how do they measure how well the editing models actually do on these complex instructions? What are the metrics?
They came up with a solid evaluation framework using 3 main metrics. The first is instruction following, or IF.
IF. Does it just mean, did the model do what was asked?
Pretty much, yeah.
Yeah.
How accurately were the specified changes made in the output image?
Makes sense. What's number 2?
Second is identity preservation, IP. This one is crucial.
Identity preservation. Keeping things the same.
Exactly. Did the parts of the image that shouldn't have changed actually stay unchanged? You don't want the model messing up the background when you just asked it to change the cat's color.
Right, avoiding collateral damage.
Yeah.
And the third metric.
Third is perceptual quality, PQ. This looks at the overall visual quality of the final image.
So does it look good? Does it look realistic, artifact-free?
Yeah, things like lighting consistency, how well new elements are blended, are there weird distortions, the overall aesthetics.
Okay, IF, IP, and PQ. How do they actually calculate these scores, especially at scale? Must be a lot of images.
They automated it using a vision language model, a VLM.
Using AI to judge AI.
Huh? Yeah, essentially. They feed the VLM the original image, the edited one, and the instruction. The VLM then outputs a score from 0 to 10 for each metric IF, IP, and PQ.
How do they make sure the VLM scoring is consistent? It feels like judging quality could be subjective.
Good point. They developed very detailed rubrics for each score level. So the rubric spells out exactly what a 7 in perceptual quality means versus a 6 or an 8. It gives the VLM clear guidelines.
Okay, detailed rubrics help standardize the VLM's judgment. They also mentioned looking into different ways the VLM calculates the score, numeric versus token probability.
Yeah, they tested two ways. One was just asking the VLM directly for a number, 0 to 10, that's numeric scoring.
And the other?
The other, token probability, was phrasing it like a yes-no question and using the probability the VLM gave for yes. But they found numeric scoring worked better, especially with those detailed rubrics backing it up.
Interesting. And they evaluated each image multiple times to handle variability in the VLM.
Exactly. Even advanced VLMs like GPT-4o or Gemini can give slightly different scores sometimes. So they ran 20 evaluations per sample and averaged the scores.
20 times.
Wow.
That really aims for stability.
Yeah, it helps smooth out any randomness and gives a more reliable performance measure.
Okay, solid benchmark, robust evaluation. So what did they find? What were the big technical takeaways when they tested different models?
Well, one major finding was a pretty clear performance gap between the open source models they tested, like UltraEdit, Omnigen, and the proprietary ones, like Imagen 3 or C-Edit.
A gap. How significant?
Quite noticeable. And importantly, this gap tended to get wider as the instruction complexity increased from C1 up towards C8.
So the harder the instruction, the more the open source models fell behind the proprietary ones in their tests.
That's what the results indicated, yeah.
Yeah.
It suggests handling that high level of complexity is a bigger hurdle for the open source architectures they looked at.
Were there specific metrics that suffered more as complexity went up?
Yes. While instruction following IF did drop, the bigger hits seem to be on identity preservation, IP, and perceptual quality, PQ.
So as instructions got tougher, models were more likely to mess up unchanged parts of the image, and the final image just didn't look as good or coherent.
Exactly. More complex edits seem to increase the risk of unintended changes and visual artifacts or inconsistencies.
That kind of makes intuitive sense. More moving parts, more chances for things to go wrong. What about trying to break down the complex instructions? Did that help?
Yeah. They tested that applying the atomic instructions one by one sequentially, like a chain of thought for editing.
You'd think that might make it easier, right?
Yeah.
Smaller steps.
You would, but actually they found the opposite. Sequential editing generally degraded performance across all metrics. IF, IP, and PQ often got worse.
Really? Why would that be?
It seems errors accumulate.
Yeah.
Small imperfections or artifacts introduced in the first step get carried over and potentially amplified in the next step, and so on. It leads to this gradual degradation.
So tackling the whole complex instruction at once was actually better, even if harder.
In their experiments, yes, direct editing generally outperforms sequential editing.
But they did find some way to improve results, using a best-of-n strategy.
Correct. They tried generating multiple outputs NA4 in their tests for a given instruction, and then picking the best one according to their VLM evaluation score.
Like generating 4 possible edits and choosing the one the VLM ranks highest.
Exactly. And that did help. It improved results for both direct editing, and it helped mitigate some of the degradation in sequential editing, particularly boosting instruction following and perceptual quality.
So generating options and picking the best is a viable technique to squeeze out better performance.
Seems so. It's a test time strategy that can improve things without retraining the model itself.
Now, there's this other interesting point, the curse of synthetic data. What was that about?
Yeah, that was fascinating. They observed that some models, particularly those known or suspected to be trained on lots of synthetic image data.
Like AI-generated training images.
Right. Those models tended to produce edits that looked increasingly artificial or synthetic as the instruction complexity increased, even when starting from a real photo.
So the more complex the edit, the less realistic the output looked, specifically for models trained heavily on synthetic data.
That was the trend they noticed. And Interestingly, they even saw hints of this with powerful proprietary models like Imagen 3 and GPT-4o at the very highest complexity levels, like C8.
Wow. So even the best models might start showing this effect if they rely too much on synthetic training data when pushed really hard.
It suggests that, yeah, it points to a potential challenge in training data composition. How do you train models to be robust to complex instructions without losing that touch of realism?
That's a really important technical consideration for developers, the balance between capability and realism.
Definitely. It suggests that maybe the type of data used for training really impacts how well the model generalizes to complex real-world editing scenarios while maintaining visual fidelity.
So wrapping this up, this complex edit benchmark seems like a really valuable contribution. It highlights that handling truly complex instructions well is still a major technical hurdle.
Absolutely. We've come a long way with simple edits, but this work shows there's still a significant gap when it comes to intricate, multi-step transformations while keeping everything looking right.
The systematic benchmark generation and the detailed evaluation metrics IF, IP, PQ give the research community much better tools to measure progress.
For sure. And the findings are key. The performance gaps, the specific impact of complexity on IP and PQ, this potential curse of synthetic data, these are all crucial technical insights.
Plus, the experiments with sequential editing versus direct and the best of N approach point towards strategies for improving current models.
Right, they offer practical avenues for trying to boost performance at test time.
It really leaves you thinking about the next steps. How do we design training data, or maybe even model architectures, to overcome these limitations that complex edit has exposed? Achieving truly robust, realistic, complex editing is still a major technical goal.
Indeed, it underscores that while progress is rapid, mastering the nuances of complex, instruction-based image manipulation is still very much an active and challenging research area.
Well, this has been a fascinating deep dive for listeners wanting to get into all the technical specifics. The full paper is on ArcSPIF, and we'll link it on our webpage. It's definitely worth exploring the details and the visual examples they provide.
Agreed. Lots of interesting technical detail in there.
Thanks for joining us on Neural Intel for this exploration of complex image editing.